beyond our solar system, orbiting distant stars, there are worlds we have only just begun to find. Thousands of them. Some are giants made of gas. Others are small and rocky, not so different from Earth. Tonight, we explore the strangest and most fascinating of them all. For most of human history, we had no proof that planets existed around other stars. We assumed they did. It seemed unlikely that our sun was the only star in the galaxy with a family of worlds. But assuming and knowing are very different things. The first confirmed discovery of a planet orbiting a sun-like star came in 1995. Two Swiss astronomers, Michel Mayer and Didier Queloz, detected a planet orbiting the star 51 Pegasi, about 50 light-years from Earth. The planet was roughly half the mass of Jupiter, and it orbited its star in just 4 days. 4 days. That meant it was orbiting incredibly close to its star, far closer than Mercury orbits our sun. This was a shock. No one had predicted that a gas giant could exist so close to a star. In our solar system, the gas giants, Jupiter, Saturn, Uranus, and Neptune, all orbit far from the sun, in the cold outer regions where ice and gas could accumulate during the solar system's formation. A Jupiter-sized planet orbiting closer than Mercury seemed impossible. And yet, there it was. The first of a new class of planets that astronomers would come to call hot Jupiters. Giant worlds, roasting in the heat of their parent stars, orbiting so fast that their years last only a few Earth days. This single discovery changed everything we thought we knew about how planetary systems form. And it was only the beginning. Since 1995, we have discovered over 5,000 confirmed exoplanets. The number grows every month. And the variety of worlds we have found is staggering. There are planets made almost entirely of water. Worlds where the ocean has no floor, stretching down for hundreds of kilometers until the pressure compresses the water into exotic forms of ice. There are planets where it rains molten glass. Sideways, driven by winds that blow at thousands of kilometers per hour. The planet HD 189733b has an atmosphere so hot on its day side that silicate minerals evaporate into gas. On the night side, temperatures drop enough for those minerals to condense into tiny glass droplets, which are then swept across the planet by supersonic winds. A rain of molten glass, flying horizontally through a sky of fire. There are planets that orbit 2 stars at once. World where you would see 2 suns in the sky, one large and one small, circling each other as they cross the heavens. These circumbinary planets were once thought to be impossible, too gravitationally unstable to survive. But the Kepler Space Telescope proved that they exist and that they may be surprisingly common. There are planets so close to their stars that they are being slowly torn apart. Their atmospheres are being stripped away by intense radiation, leaving a trail of gas behind them like a comet's tail. These are the evaporating planets, worlds caught in the process of being destroyed, visible to us only because we happen to look at the right time. And there are planets that seem almost like home. Rocky worlds, roughly the size of Earth, orbiting within the habitable zone of their star. The region where temperatures might allow liquid water to exist on the surface. These are the planets that capture our imagination most of all. Because where there is liquid water, there might be life. How do we find these worlds? They're so far away that even the most powerful telescopes cannot see them directly. Exoplanets are tiny, faint, and completely overwhelmed by the glare of their parent stars. It is like trying to spot a firefly hovering next to a searchlight from 1,000 kilometers away. The most successful method is called the transit method. When a planet passes in front of its star, as seen from Earth, it blocks a tiny fraction of the star's light. This dip in brightness is small, often less than 1%, but it is measurable with sensitive instruments. By observing thousands of stars simultaneously and watching for these periodic dips, astronomers can detect planets that would otherwise be completely invisible. The Kepler Space Telescope, launched in 2009, used this method to revolutionary effect. It stared at a single patch of sky for 4 years, monitoring the brightness of over 150,000 stars. In that data, it found thousands of planets. Kepler showed us that planets are not rare. They are everywhere. On average, every star in a galaxy has at least one planet. Some have many more. Another method is the radial velocity technique. As a planet orbits a star, its gravity pulls the star slightly, causing the star to wobble. This wobble shifts the star's light toward the red end of the spectrum when the star moves away from us, and toward the blue end when it moves toward us. By measuring these tiny shifts, astronomers could determine the mass and orbit of the planet causing the wobble. This was the method used to discover the very first exoplanet around 51 Pegasi. It is less effective for small planets, whose gravitational pull is too weak to cause a detectable wobble, but it remains a powerful tool for discovering large planets close to their stars. More recently, astronomers have begun to directly image exoplanets. By using special instruments called coronagraphs that block the light of the star, they can sometimes see the faint glow of a planet orbiting beside it. This is extraordinarily difficult, and it has only been achieved for a handful of large, hot planets orbiting far from their stars. But the technology is improving rapidly. Future telescopes may be able to directly image Earth-sized planets around nearby stars. Among the thousands of exoplanets discovered, a few stand out as particularly remarkable. TRAPPIST-1 is a small, cool red dwarf star about 40 light-years from Earth. It is orbited by 7 rocky planets, all of them roughly the size of Earth. 3 of these planets orbit within the habitable zone, where liquid water could exist on the surface. 7 Earth-sized worlds, 3 of them potentially habitable, all packed into a system so compact that the outermost planet orbits closer to its star than Mercury orbits our Sun. If you stood on the surface of one of the TRAPPIST-1 planets, the other planets would be visible in the sky. Not as faint points of light like planets appear from Earth, but as disks. Some would appear larger than our moon. You could see their surface features with the naked eye. It would be unlike anything we have ever experienced. Kepler 452b was one of the first Earth-sized planets found in the habitable zone of a Sun-like star. It orbits a star very similar to our Sun, at a distance very similar to Earth's. Its year is 385 days long, almost identical to ours. It is often called Earth's cousin, though we know very little about its actual conditions. It could be a rocky world with oceans and an atmosphere. Or it could be a barren, lifeless rock. We simply do not know yet. 55 Cancri E is a world that may be partially made of diamond. It is a super Earth, about twice the size of our planet, orbiting so close to its star that its surface temperature reaches nearly 2,000 degrees. At these temperatures and pressures, the carbon in the planet's interior may crystallize into diamond. An entire world where the ground beneath your feet might be made of the hardest natural material known to science. And then there is PSRB 1257 plus 12. This planet does not orbit a normal star. It orbits a pulsar, the rapidly spinning remnant of a star that exploded as a supernova. This was actually the very first exoplanet ever detected, discovered in 1992, 3 years before the discovery around 51 Pegasi. But because it orbits a dead star rather than a living one, it was considered a special case. It is a world born from destruction. A planet that formed from the debris of a stellar explosion orbiting a corpse. One of the most profound questions raised by the discovery of exoplanets is whether any of them harbor life. We do not know the answer. Not yet. But we're closer to finding out than ever before. The James Webb Space Telescope, launched in 2021, is capable of analyzing the atmospheres of exoplanets by studying the light that passes through them during transits. Different gases absorb different wavelengths of light. By examining which wavelengths are missing from the starlight that filters through a planet's atmosphere, astronomers can determine what gases are present. If we detect oxygen, methane, and water vapor in the atmosphere of a rocky planet in a habitable zone, it would be a strong hint that something biological is happening on the surface. These gases, in combination, are difficult to produce and maintain without life. They would not be proof, but they would be the strongest evidence we have ever had. The search is already underway. JWST has already begun studying the atmospheres of several promising exoplanets, including some of the TRAPPIST-1 worlds. The data is complex and difficult to interpret, but every observation brings us a little closer to an answer. Within our lifetimes, we may know whether the building blocks of life exist on worlds beyond our solar system. We may not find little green creatures. We may not even find microbes. But we may find the chemical signatures that suggest life is possible. And that alone would change the way we think about our place in the universe. The sheer number of exoplanets is perhaps the most humbling fact of all. There are roughly 200 billion stars in the Milky Way. If every star has at least one planet, that means there are at least 200 billion planets in our galaxy alone. And there are at least 2 trillion galaxies in the observable universe. The total number of planets in the universe is a number so large that it has no intuitive meaning. Trillions upon trillions upon trillions. Among all those worlds, it seems almost impossible that Earth is the only one where the chemistry of life has taken hold. The universe is too vast, too old, and too creative for that to be true. Somewhere out there, orbiting a star we may never see, there's probably a world where something is alive. Something that looks up at its own sky and wonders if it is alone. We may never meet them. The distances are too great. The speed of light is too slow. But knowing that they might exist somewhere changes everything. It means the universe is not just a collection of rocks and gas and radiation. It is a place where matter can wake up, look around, and ask questions about itself. And that is perhaps the most extraordinary thing any planet, anywhere has ever done. But let us not get ahead of ourselves. Finding a planet in the habitable zone does not mean it is habitable. The habitable zone is defined only by temperature. It is the distance from a star where liquid water could exist on a rocky planet surface. But temperature alone does not make a world friendly to life. A planet needs an atmosphere to keep water liquid. Without atmospheric pressure, water boils away into space, even at moderate temperatures. Mars sits at the edge of our sun's habitable zone, but its atmosphere is so thin that liquid water cannot survive on its surface for more than a few moments. It evaporates almost instantly. A planet also needs a magnetic field to protect its atmosphere from the solar wind, the stream of charged particles that flows constantly from its star. Without a magnetic field, the solar wind gradually strips the atmosphere away, molecule by molecule, over millions of years. This is probably what happened to Mars. It once had a thicker atmosphere and liquid water on its surface, but without a strong magnetic field to protect it, the atmosphere was slowly eaten away. And a planet needs the right chemistry. An atmosphere of pure carbon dioxide, like Venus, creates a runaway greenhouse effect that raises temperatures to over 450 degrees. An atmosphere with too much methane or ammonia might be toxic to the kinds of life we know. The balance of gases matters enormously. So when we say a planet is in the habitable zone, we are really saying it has passed the first test. The temperature test. But there are many more tests after that. Atmosphere. Pressure. Chemistry. Magnetic field. Stability. Liquid water on the surface is not a given. It is a possibility. And the difference between possibility and reality is often enormous. This is why finding biosignatures, chemical signs of life in an exoplanet's atmosphere, would be so significant. It would tell us not just that a planet could support life, but that it does. Or at least that something on its surface is producing the kinds of gases that life produces on Earth. There's another class of exoplanets that we have not yet mentioned. Worlds that do not fit neatly into any category we know from our own solar system. Super-Earths are planets with masses between 1 and 10 times the mass of Earth. They are larger than Earth, but smaller than Neptune. And they're the most common type of planet in the galaxy. Our solar system has nothing like them. We go straight from Earth to Neptune with nothing in between. But out there, around other stars, super-Earths are everywhere. Some super-Earths may be scaled-up versions of our own planet. Rocky, with thin atmospheres, possibly with oceans and continents. Others may be mini Neptunes, wrapped in thick envelopes of hydrogen and helium, with no solid surface at all. The boundary between a large rocky planet and a small gas planet is not clear, and it is one of the big open questions in exoplanet science. Sub-Neptunes are similar. They're smaller than Neptune, but larger than Earth, and they seem to have thick, puffy atmospheres that make them look bigger than they actually are. What lies beneath those atmospheres is a mystery. There could be a rocky surface under all that gas. Or there could be an ocean of water, or something even more exotic, like an ocean of supercritical fluid, a state of matter that is neither truly liquid nor truly gas. We do not have the tools to see beneath these atmospheres. Not yet. But future telescopes and future missions will peel back those layers, one by one, revealing what lies beneath. There are also worlds that exist in total darkness, not because they are rogue planets without a star, but because they are tidally locked. A tidally locked planet always shows the same face to its star, just as our moon always shows the same face to Earth. One side is permanently lit, baking in endless daylight. The other side is permanently dark, frozen in endless night. The boundary between the two sides, called the Terminator line, is a narrow strip of perpetual twilight. Some scientists believe this strip could have the most moderate temperatures on the planet. Not too hot. Not too cold. A ring of habitable territory circling the planet between fire and ice. Many of the rocky planets found around small red dwarf stars are likely tidally locked. Red dwarfs are the most common type of star in the galaxy, and their habitable zones are very close to the star, which makes tidal locking almost inevitable. If life exists on these worlds, it may cling to the edges, living in the permanent twilight between two extremes. The idea of a world divided into eternal day and eternal night is both strange and beautiful. A planet where the sun never sets on one side and never rises on the other. A world where the concept of morning and evening has no meaning. Where weather patterns are driven not by the rotation of the planet, but by the temperature difference between the burning day side and the frozen night side. We have no thing like this in our solar system. But in the galaxy at large, these worlds may be among the most common habitable environments that exist. The search for exoplanets has taught us something that goes beyond any individual discovery. It has taught us that the universe is far more imaginative than we are. Every time we thought we understood how planets work, the universe showed us something we did not expect. Hot Jupiters, diamond worlds, lava planets, tidally locked worlds, planets orbiting dead stars, planets orbiting two stars, planets with no star at all. Every assumption we brought from our own solar system has been challenged, revised, or overturned. The universe does not build solar systems according to a template. It builds them according to physics and chance, and the results are endlessly varied. Our solar system is not typical. It is one example out of billions, and it may turn out to be one of the less interesting ones. That is a humbling thought, but is also an exciting one, because it means that the universe still has surprises waiting for us. Worlds we have not imagined, conditions we have not predicted, possibilities we have not considered. Every new exoplanet we discover is a reminder that we are still at the very beginning of understanding what the cosmos has created. Let your mind drift now. Let the distant worlds fade into the warm darkness of rest. Somewhere out there, a planet with two suns is watching them both set. Somewhere, an ocean world is stirring beneath its endless waves. Somewhere, a diamond planet is glittering in the heat of a nearby star. And here, on this small rocky world orbiting an ordinary star in an ordinary galaxy, you are resting. Safe and warm. Part of the same cosmos that built all those distant worlds. Made of the same atoms. Shaped by the same forces. The universe is full of worlds. And you are on one of the most remarkable of them all.